Welcome back, and today we're going to be talking about a type of ODE called a separable ODE. So, what is a separable ODE? A separable ODE is one that can be expressed in the following format. The format is y prime, or dy dx if you prefer, is equal to some expression containing only x's multiplied by some expression containing only y's. An expression containing only x's multiplied by an expression containing only y's. For some examples of separable ODEs, we might have something like the following. We could have something like y prime is equal to e to the x plus 4 quantity squared multiplied by 1 over y plus 4 times y. This would be equal to an expression containing only x's multiplied by an expression containing only y's. Now potentially, the differential equation may not come to you in this format. You may have to rewrite it so that it is in this format. For example, you have xy times y prime plus e to the x equals 0. This doesn't immediately appear to be in the right format, but let's try and rearrange this quantity. We can rewrite this as y prime equals negative e to the x divided by x times y, which in turn can be rewritten as negative e to the x divided by x multiplied by 1 over y. So this is separable because it can be expressed as a function containing x's only multiplied by a function of y alone. In addition, if you have something like y prime equals an expression containing only y's, maybe y squared minus 8, this would be separable. In this case, the function of x alone is just the constant function 1. And similarly, if you have something like y prime equals 3x plus 4, one of these Calc 2 differential equations, this would also be considered separable. In this case, the function of y alone would just be considered the constant function 1. But not all ODEs are separable. For example, a frustrating example of an ODE that is not separable is something like y prime equals x plus y. This is in the form function of x alone plus a function of y alone, but there is no way to rewrite this as a function of x multiplied by a function of y. So an ODE like this is not separable, and we'll have to solve it by some other means. So we have a new type of ODE. The type is called separable. We know now how to identify that type. So what is the technique that we need in order to solve this type of differential equation? So the first thing that you want to do is you want to rewrite this in the form 1 over f of y times the y prime equals gx. Basically, leave your gx on the right side of the equation isolated, but pull your fy over to the left side of the equation together with your y prime. That's the first step. The next thing that you want to do is you want to integrate both sides of the equation with respect to x. Now when you do this, what you're going to get is an expression that looks like the following. The integral of 1 over f of y times dy dx integrated with respect to x is equal to the integral of g of x with respect to x. Now here's the big trick. You're going to want to replace the product dy dx times dx on the left-hand side with just dy. Almost as if you were cross-canceling the two dx's. That's not really what you're doing. Technically what you're doing is almost a substitution. What you called in Calc 2 U substitution. But in practice, no one really thinks about this in those terms. We really kind of think about it as canceling the two dx's, cross-canceling these two dx's. So what you're left with is an integral of the left side with respect to y and an integral of the right side with respect to x. So to finish solving the separable ODE, all that you need to do is complete the integration and then solve for y. Let me show you what I mean. So let's go ahead and let's solve the ordinary differential equation y prime equals x over y. So the first thing that I'm going to do is I'm going to rewrite this so that the function of y alone is on the left-hand side of the equation and the function of x alone is on the right-hand side of the equation. So I'm going to move that y over by multiplying both sides by y. This is going to give me y times dy dx equals x. Now I'm going to go in and take the integral of both sides with respect to x. But I'm going to transform that y prime dx into a dy. So on the left side, I'm going to integrate y with respect to y, and on the right side, I'm going to integrate x with respect to x. So when I do that, the left side becomes y squared over 2 plus c, and the right side is going to become x squared over 2 plus c. But it's inappropriate of me really to use c plus c on both sides because these two c's could be different. To acknowledge the fact that they could be different, I'm going to give them different subscripts, c1 and c2. Alright, I went and made a little bit more space for myself. So now I'm going to begin the process of solving for y. So I'm going to go ahead and boot that c sub 1 to the right side of the equation. Y squared over 2 is equal to x squared over 2 plus c2 minus c1. Now we're going to begin a time-honored tradition in differential equations of combining constants. If c2 is an unknown constant and c1 is an unknown constant, then c2 minus c1 is just going to be some other unknown constant. So let's just, for simplicity's sake, combine those into a unified single unknown constant called plus c. So still in pursuit of solving for y, let's go ahead and multiply everything by 2. But again, let's use the same idea. If c is some unknown constant, then 2 times c is just going to be some other unknown constant. So writing 2c is kind of useless, since c just is a stand-in for some arbitrary unknown real number. Instead of 2c, we'll combine to just another refreshed plus c. So now the only thing that remains is to get rid of the square on y. Y is equal to plus minus the square root of x squared plus some arbitrary unknown real number. This is the format of all possible solutions to the original differential equation. So that's the general process for solving a separable ODE. Get all the y's over to the left and get all the x's on the right. Integrate both sides, solve for y. You do have to be a little bit careful when you are moving the y's to the left side. For example, in a problem like this one, r is some real number, whatever it might be. Let's solve the ODE y prime equals r times y. One way to get this function into the right format is to divide both sides by y. But the problem is that you can only divide both sides by y if y is not 0. The problem is that y equals 0 is actually a perfectly valid solution to this differential equation. Because if I take the derivative of 0, the result of that is 0, and 0 is equal to r times 0. So I'm going to go ahead and divide by y. To get my function into the right format, 1 over f of y times y prime equals g of x. But I'm just going to acknowledge the fact that y equals 0 is also a solution. I'm going to acknowledge that in a separate step. So having separately noted that, then it's safe for me to divide both sides by y to get the ODE into the correct format. 1 over function of y times y prime equals g of x. In this case, g of x is just the constant r. So now it's safe for me to go about the next step in the process, integrating both sides. Now this is where you're going to see me begin to skip a few steps. For example, rather than integrating both sides with respect to x, and then replacing y prime dx with a dy, you're going to see me directly integrate 1 over y with respect to y. So when I do this, the left side becomes the natural log, absolute value of y, and the right side becomes r times x plus c. Notice that I skipped a step in this line as well. In the previous problem, I wrote a plus c1 on the left side and a plus c2 on the right side. However, that action didn't really end up being valuable because I ended up combining my c2 and c1 into a unified c on the right-hand side. So I have in total skipped 2 steps, and you're welcome to skip these steps as well. So now, having skipped those steps, let's go ahead and proceed to solve for y. I need to get rid of natural log, which means that I need to employ the natural exponential. E to the power rx plus c. Raise everything on the right-hand side so that it's an exponent on e, which means that y could be equal to plus or minus e to the rx plus c. Now this is a perfectly valid way to express the complete set of functions which are solutions to the given ODE. But there's a more traditional way to express these solutions to this problem. The traditional way is to say, okay, By the properties of exponents, if you have a sum at the exponent level, you can turn that into a product at the base, e to the rx multiplied by e to the c. So now what we're going to do is we're going to combine constants again. In particular, we're going to combine the constants plus minus e to the c. If you raise c to some unknown real number, then you're going to get some other unknown real number. If you plus minus that, again, you're still just going to get some real valued constant. So we combine this into an expression which is usually written in the form k times e to the rx. I don't know why they're using k instead of c, but this is just tradition. So, what do the solutions to the ODE y prime equals number times y look like? They look like k times e to the rx. For example, if you're solving y prime equals 4 times y, now we know that those solutions look like k times e to the 4x. In the specific case where y is multiplied by 4, the coefficient in the exponent is also 4 to match. One more example to demonstrate the method. Let's solve the ODE y prime equals y squared minus 4. Now let me ask you a question. Do you think I could approach this problem by subtracting y squared to the left side to get it on the same side as y prime? This is not going to work. In order to use the method of integration, we need to have a function of y multiplied by y prime, not added or subtracted. So we won't be able to subtract y squared. We're going to have to divide, and in this case, in order to get a function of y on the left-hand side and no y's on the right-hand side, we're going to need to divide by the entire quantity, y squared minus 4. If we divided just by y squared, that would leave a y squared in the denominator under the 4. So that's not going to work. In order to get all the y's over to the left side in the correct format, we have really no other choice except for to divide by everything y squared minus 4. But we have to be careful. We just divided both sides of an equation by something that contains a variable. So we need to consider the case separately that the thing that we just divided might be 0, which would mean that y would be equal to either plus or minus 2, these two constant functions. Now in each case, y prime would be equal to 0. And in each case, y squared minus 4 would be equal to plus or minus 2 minus 4 would be equal to 0. So actually, the two constant functions, y equals plus minus 2, are both solutions. Okay, so now that we've made a separate note of these two solutions which make this denominator 0, let's go ahead and proceed with the assumption that the denominator is not 0 and integrate both sides of this equation. So in order to integrate 1 over y squared minus 4, we'll need to split up this fraction using partial fraction decomposition, all the way back from Calc 2. So 1 over y squared minus 4 could be split apart as the sum of two fractions, if I factor the denominator, I get y minus 2, y plus 2. And so I can split up this as the sum of a number divided by y minus 2 plus a number divided by y plus 2. I'm going to fill in the blanks using the Heaviside cover-up method. I will put a link in the description if you are not familiar with this method. So I'm going to cover up y minus 2 on the left side, plug in y equals positive 2, and I get 1 over 4. Y equals negative 2 is what makes the second denominator 0, and I get 1 over 4 negative. So on the left-hand side, I'm integrating 1/4 y minus 2 plus negative 1/4 y plus 2 with respect to y. That's equal to the integral of 1 with respect to x. So the left side becomes 1/4 times the natural log of y minus 2 minus 1/4 natural log of y plus 2 is equal to x plus some unknown arbitrary constant. So let's go ahead and multiply everything through by 4. To clear out those 1/4, and I get 4x plus 4 times c, but what I'm going to do is I'm going to combine 4c and do a new arbitrary constant. Now with natural log of y minus 2, take away natural log of y plus 2. This is a prime opportunity to combine these two logarithms. So a subtraction outside the log becomes division inside the log, and I'm looking at the natural log of the absolute value of y minus 2 divided by y plus 2. Let's go ahead and apply e to both sides to get rid of that natural log. And let's go ahead and apply plus minus to both sides. And let's go ahead and get rid of those absolute values using a plus minus. And I'm going to use the same trick for combining constants that we used in the previous example. Instead of having an e to the 4x plus c, I'll think about this as e to the c times e to the 4x, and I'll combine these constants into a single united k. So now I have y minus 2 over y plus 2 equals k e to the 4x. So now all that's left is algebra really. Let's go ahead and clear these fractions. Let's go ahead and gather all the terms containing y, isolate all the terms that don't contain y, and then factor and divide. So in this case, this would be the form of a general solution to the differential equation above. Either y has the format of this fraction, or y could be equal to the two solutions plus or minus 2, the two constant valued solutions, which we found by considering separately the case that would be causing us to divide by 0 in our initial step. That concludes today's material. We introduced a new type of differential equation, which was called separable. A separable equation could be solved by bringing all the y's to one side of the equation, leaving all the x's on the other side of the equation, in such a way that you had an equation of the form function of y times y prime equals g of x. Then you can solve the equation by integrating. Integrate the y's with respect to y, integrate the x's with respect to x, and then algebraically solve for y.